Dear professors and students, it's a great honor for me to have the online speech today. On behalf of our research group, I will share the research on concrete filled square steel tubular structures with inner I-shaped CFRP with you. I will talk about the 5 items. With the continuous growing of the population and the expansion of urbanization, the demand for the building numbers and its performance are higher than before. This will cause attention in urban land using. Therefore, there are 2 problems needed to be solved with the development of the technique. The tension of the urban land using and how to improve building performance. We build high-rise buildings and high-performance buildings to solve the 2 problems above. For the system of the structure, high-performance buildings should be studied and applied. The steel and concrete composite structure makes full use of the good properties of the 2 materials to improve the performance of members. Hence, a question has arisen: how to further improve the performance of the traditional composite structures? We put CFRP profile into traditional CFST to achieve the effect of 1 + 1 + 1 greater than 3. The composite structure has many advantages for its mechanical performance. It can improve the deformation performance, that is, ductility of the member. In particular, after the member has achieving its peak load or the ultimate bearing capacity, the right steel bearing capacity is much higher than that of the traditional CFST. This is very important for us to improve the collapse resistance of the structure in face of the disasters, which can save more lives. Therefore, this new type of member is particularly suitable for various important structures or important columns of the structure. Before the production of FRP profile, the size is first designed through finite element analysis. After that, the FRP was produced. It is firstly impregnated into the resin, then powder-treated to form the FRP profile through a processing mode. By testing the FRP, a powder-treated board is tensile strength and compressive strength is 3.4 times and 2.5 times the yield strength of S355 steel, respectively. Therefore, its excellent compression performance can be fully utilized, and the constitutive relationship is still linearly elastic. Combined with the finite element analysis and experimental results, the strength criteria of the profile are determined, which has laid an important theoretical basis for the analysis of the following members. Regarding the constitutive relationship of composite materials, we define the strength criteria of the composite materials through the corresponding characteristic points at each stage of the strength failure process. Then, on the basis of proposing the double composite effect coefficients, the character value, proportional limit, elastic modulus, tangent modulus, and the other indexes of the composite materials are established. The second issue that needs attention is the working mechanism of composite member. In this presentation, we'll focus on 4 key techniques. The first technique involved is the cooperative working mechanism of each composite. During the entire loading process of the axially compressed stop column, the stress of the 3 materials increases linearly in the elastic phase. However, in the elastoplastic stage and the plastic hardening stage, due to the longitudinal cracks and expansion of the core concrete, FRP profile and steel tube have double constraints on the core concrete. At the location of the profile and the corner of the cross-section, a very obvious restraint effect is observed, which significantly increases the stress of the concrete in the two areas. In the descending stage, damage to the core concrete was found through analysis, and the damage gradually occurred from the edge of the constrained interface to the center of the section. Finally, after the core concrete is crushed, the profile is destroyed. Ideally, the method and order of the destruction of this material are exactly what we want. This is because throughout the destruction process, the three materials have given full play to the strength characteristics of each material. We also eccentrically compress the columns as well as the pure bending member. From the perspective of stress analysis, the whole process analysis shows that the three materials can fully exert their material properties. The second technique is the plane section assumption. In fact, this is a very simple concept, but very important. If the members do not meet the assumptions, many calculation methods and formulas cannot be used. The third technique is the moment of the neutral axis. It will reflect the characteristics of the deformation and the failure of various members during the entire loading process. Through the analysis of the moment for stub columns and long columns under the eccentric compression, it shows that two factors of eccentricity and the slenderness ratio have the greatest influence on the moving speed of the neutral axis. For pure bending members, the moving speed of the neutral axis is analyzed through each stage of the whole loading process. When the neutral axis is within the range of the FRP profile web, the moving speed is relatively slow. This is because the profile itself basically forms a self-balance, which limits and delays the development of the compression zone in height. The last technique is the analysis of restraint effects, which reflects the cooperative working mechanism of the three materials. These figures describe the stress contours of stub and long columns under axial compression. After the steel yields, the profile itself has a very significant restraint effect on the concrete. At the same time, this interaction acts as a support to the inner CFRP, so it can give full play to its compression performance. After reaching the peak loss, the stress gradient gradually accelerates from the center of the interface to the edge, indicating that the restraint effect is gradually reduced. In addition, the stress contour of the long column has a strip distribution, indicating that the restraint effect of the axially compressed long column is lower than that of the subcolumn. Moreover, the unidirectional eccentrically compressed member is analyzed. The stress contours in the tension zone is relatively evenly distributed in chips. Well, an ambulance-shaped distribution appears in the compression zone. In the confined area, the strength of the concrete has been significantly improved. As the stress increases, the scope of its distribution gradually increases. The restraint effect of bidirectional eccentrically compressed member is weaker than that of unidirectional eccentrically compressed member. Therefore, the effect of constraints can be summarized as follows. From the perspective of restraint effect, the FRP profile and steel tube produce a relatively ideal restraint effect on the core concrete, therefore improving the bearing capacity of the composite structure and the ductility as well. Based on the previous theoretical analysis, calculation method for various composite structures are proposed. Several codes for stub columns and axial compression are compared. It turns out that the codes from China and Europe are relatively suitable, but there are still some discrete data. Therefore, our team established a recommended calculation formula. For long columns, when a certain slenderness ratio of the elastic buckling of the composite structure has been determined, a quantitative relationship between the stability factor and the slenderness ratio is established. For the calculation method of unidirectional eccentrically compressed long columns, the influence of the slenderness ratio and the second-order effect is considered. Considering the double restraint effect for the bidirectional eccentrically compressed column, the coordinates of the balance point is determined, and the design method is established. Regarding the pure bending member, the composite constraint effect coefficient is introduced, and the quantitative relationship between the plastic development coefficient and the composite constraint effect coefficient is estimated. To summarize it simply, these three materials produce a very good composite effect, give full play to the advantages of the materials, and significantly improve the strength and deformation of the building. Finally, I would like to thank the National Natural Science Foundation of China for its support. Also, I would like to thank my team members, Professor Haixia Zhang, Associate Professor Zhijian Yang, Lecturer Zheng Meiqiu, and my PhD students Bowen Chen, Xiao Li, Runzhe Liu, and numbers of graduate students. This concludes my speech today. Thank you for your listening.